All right, objective 5. So solve system of 3 equations containing 3 variables. So systems of linear equations containing 3 variables have the same number of possible solutions as system of 2 linear equations containing 2 variables. 1, exactly one solution, a consistent system with independent equations. 2, an inconsistent system. And 3, infinitely many solutions. A consistent system with dependent equations. The graph of each equation in a system of linear equations containing 3 variables is a plane in space. A system of 3 linear equations in 3 variables represents 3 planes in space. The following figure illustrates some possibilities. So for A, we have a consistent system where 3 planes intersect at one solution. For B, we have a consistent system with infinitely many solutions where you could have 3 planes that intersect along a line, and a line has infinitely many points, therefore infinitely many solutions. Or we could have 3 equations that represent 3 planes that are actually the same equation. And then for C, we could have an inconsistent system where we have no solution, where all 3 planes are parallel to each other, meaning there's no intersection, or all 3 pairs don't share one exact intersection line or solution. Okay. So a solution to a system of equations consists of values for the variables that are solutions of each equation of the system. For the 2 variable case, these solutions were given as ordered pairs. For a 3 variable case, such solutions will be given as ordered triples. For this example, we have the point 3, -1, and -5, where x is 3, y is -1, and z is -5. And we need to show that this point is a solution to the system. So this is a 3 equation system. So we are going to substitute each of these coordinates into each equation to determine whether it makes that equation true, so that statement true. If it does, then we know it's a solution to that equation. Now it has to be true for all 3 equations in order for it to be a solution for the whole system. So let's substitute in these values. So we'll substitute in 3 for x, -1 for y, and -5 for z. So I'm going to substitute it all in first before I simplify. You can definitely do it all one at a time if you like. And +5, -1, and I want to know if that equals 14. Okay, so now we can simplify. So 3 minus 1 minus 5. So that's 2 minus 5, which equals -3. That's true. So we have 6 plus 3 minus 15. No, not 15. That would be 30. 30. So that would be 9 minus 30, which would equal -21. So that's true. Then we have -9 minus 5, which is -14, which is true. So we know the ordered triple, 3, -1, -5 is a solution to this system. Okay. So for 3 variable systems, we can again solve systems algebraically using either the method of substitution or the method of elimination. Okay. Typically, the method of elimination is preferred. And that's because it is a three equation system. But you can definitely use substitution if you like. So for this example, we are going to be using the elimination method, and we have some steps here that we're going to follow to help us solve this system of three linear equations. So we have equation 1, 2, and 3, and the first thing it's asking us to do is to start by eliminating the variable x from equations 2 and 3. Okay, so in order to eliminate the variable x from equations 2 and 3, I'm going to need to multiply one of these equations by its additive inverse so that I can then add them together and eliminate the variable x. So this is going to be done in 2 steps because we add only 2 equations together, not 3. So the first thing that I'm going to do is I'm going to multiply equation 1 by -4 and then add it to equation 2. That way I'll be able to eliminate the variable x. The second thing that I'm going to do is I'm going to multiply equation 1 by -2 and add it to equation 3 so that I can then eliminate the variable x in that equation as well, which will then give me 2 new equations. Okay, so let's do that. Let's do the first one. So I'm going to multiply equation 1 by -4. So I'll do that on the left side and on the right side. So that's -4x minus 4y minus 4z equals -8. So I now have a new equation. We'll give that equation 4. So I have -4x minus 4y minus 4z equals -8. And I'm going to add it to equation 2. So 4x plus 2y minus z equals -3. And that's going to give me the equation -2y minus 5z equals -11. Okay. Alrighty. So now let's do the same thing for the next set. So I'm going to take my equation number 1 and multiply it by -2. Okay, on both sides. So I have -2x minus 2y minus 2z equals -4. Okay, so this is my new equation 5. So -2x minus 2y minus 2z equals -4. I'm going to add it to equation 3. So it's 2x minus 6y minus 5z equals -1. And I will now have -8y minus 7z equals -5. Okay, so I now have 2 new equations here. So I have 6 and 7. So now my system is x plus y plus z equals 2. That's equation number 1. And then I have -2y minus 5z equals -11. That's 6. And -8y minus 7z equals -5. And that's 7. Okay. So, but I've eliminated the x variable from equations 2 and 3. So when you're working with 3 systems, you have to figure out which equation you can use to manipulate, meaning multiply or divide it by a non-zero, in order to help you eliminate the variable in the other two equations. Okay. So now we're going to concentrate on the new equations 2 and 3. So their 2 and 3 here are going to be these right here. And the notes, as well as your textbook, as well as the presentation here, all label the values differently. The equations differently. I like to just number any new equation that I create as I go along. That way I know exactly what I'm referring to. If you have a better way of labeling, by all means, do what you feel is comfortable as long as you know what you are referring to. Okay, so the new equations for 2 and 3 that they're talking about are going to be our equations 6 and 7. Okay, so we are going to concentrate our two new equations for 2 and 3, treating them as a system of two equations containing two variables. So let's rewrite that system here. So we have negative y minus 5z equals negative 11, and negative 8y minus 7z equals negative 5. Okay, those are our two new equations that we created. And now we're going to treat it as a two-system equation. Okay, so here we can continue to use elimination or substitution, whichever one. Since our numbers don't really have a relationship, numbers that I'm referring to here are the coefficients, we're going to just stick with elimination. Okay, and so what I'm going to do is I'm going to multiply my equation. So this is 6 and 7, right? Let me make sure it's 6 and 7. Yeah, 6 and 7. All right. Multiply my equation 6 by 4, negative 4, so that I can eliminate the y variable because I have to choose one, x or y. Multiplying my first equation there, 6 by negative 4, will allow me to eliminate the y variable. I could have chosen the z variable, but then I would have to multiply both equations by a non-zero constant. And just to simplify the process, I'm going to only multiply one equation. So let's multiply the left side and multiply the right side by negative 4. So we'll get 8y plus 20z equals 44. Okay. And so now this is my new equation. So this is going to be 8. So I'm going to take equation 8 and equation 7, and I'm going to add them together. So negative 8y minus 7z equals negative 5. So my 8y and my negative 8y cancel, which leaves me with 13z equals 39. So then z equals 3. Okay. All right. So now we can solve the new equation for the remaining variable, which we did. We got z equals 3. All right, as our equation. We can now back substitute to find the values for the remaining variables. Okay, so we now know that z equals 3. So let's go back. We got that from adding equation 8 and 7 together. So to back substitute, we're now going to take 3 and substitute it into either equation 6 or into equation 7 to find the variable y. When we find the variable y, or the value for y, then we will have the value for z and the value for y, which we will then come back to our original equation up here at the top and choose an equation to substitute in z and y in order to find x. Okay, so let's first take z, which equals 3, and let's substitute it into equation 6. So that will be negative 2y minus 5z equals negative 11. So minus 2y equal, or minus 5 times 3 equals negative 11. So that's minus 2y minus 15 equals negative 11. So minus 2y equals 4. So y equals negative 2. Okay. So I have z and I now have y. So now let's choose one of the original equations to find x. And I'm going to choose equation number 1. So equation number 1 is x plus y plus z equals 2. So x minus 2 plus 3 equals 2. So x plus 1 equals 2. So then x equals 1. Okay. So I know z equals 3, y equals negative 2, and x equals 1. So the final step that we have to do is to check our answer to make sure it's a solution for all equations. Okay, so I'll rewrite our system here. X plus y plus z equals 2. Then we had 4x plus 2y minus z equals negative 3. And then 2x minus 6y minus 5z equals negative 1. So we want to check to make sure that our ordered triple, 1, negative 2, and 3, is a solution. So we'll substitute in these values, and I'm going to substitute them in first, and then I will simplify. So 4 and 1, 2, negative 2, and then 3, and then 2 and 1, negative 6 and negative 2, negative 5 and 3. So I'll have minus 2. We can just simplify that to negative 1 plus 3, which equals 2. That matches. Then we have 4 minus 3, which will get us 0 minus 3, which equals negative 3, which matches. Then we have 2 plus 12 minus 15. So that's 14 minus 15, which equals negative 1, which is true. So the ordered triple, 1, negative 2, 3, is a solution to this system. All right, objective 6, identify inconsistent systems of equations containing 3 variables. So recall that inconsistent systems have no solutions. So in this system here, we are asked to solve this system. It has 3 equations. Okay, so it's going to be very similar to the one that we just did previously. All right, so we are going to identify the variable that we want to eliminate first. Okay, and then we're going to add that to our systems. So we're going to, in other words, identify the variable, multiply, eliminate the variable, and then we have a two equation system, find another variable, then back substitute. Okay. Alrighty. So there are many ways that you can do this problem, because you could eliminate the z's, you could eliminate the y's, or you could eliminate the x's. So because the z's are right there in a parent, we are going to add those together to get our two-system equation. Okay, so we don't need to multiply anything by a non-zero constant because we have additive inverses already. So we'll match together 1 and 2, and we'll match together 1 and 3. Okay, so let's take 1 and 2, so negative 3x minus 3y plus z equals 2. Then we have 5x plus 2y minus z equals 1. So we will get 2x plus y, actually it's minus y, minus y equals 3 because the z's cancel. So that was equation 1 and equation 2. And then we'll take equation 1 and 3. So minus 3x minus 3y plus z equals 2. And x plus 4y minus z equals 3. Add those together. So we'll have minus 2x plus y, the z's cancel, equals 5. So our new system, our two equation system, is now 2x minus y equals 3 and minus 2x plus y equals 5. Okay. So now, just like in the previous problem, we are going to solve this. We could either use it using substitution or elimination, but right off the bat, I see here that I can eliminate a variable. So this is now my equation 4 and 5. So I'm going to take equation 4 and 5 and add them together. So 2x minus y equals 3 and minus 2x plus y equals 5. So the x variables cancel and the y variables cancel, which gets me 0 equals 8, which is not true. So there is no solution to this system of linear equations. So because we encounter an equation with no solution, the system is inconsistent. Okay. Alrighty. Objective 7. Express the solution of a system of dependent equations containing 3 variables. Recall that a system of dependent equations has an infinite number of solutions. So here we have another system with 3 equations and 3 variables. And we are asked to solve this system. All right. So similar to the last one, we are going to identify the variable we want to eliminate first, and then we will form our two equation system of equations to find the value of one variable, and then use back substitution to find the others in order to find our solution. Okay, so there are many ways that we can approach this problem. To help us, I'm going to utilize equation 1 as the equation I'm going to write equivalent equations for. So I'm going to take 1 and 2. I'm going to multiply 1 by negative 4. And then I'll also take 1 and 3. And I'll multiply 1 by negative 4. Because I am choosing to eliminate the x variable. Okay. So we're going to multiply equation 1 by -4. Since I'm going to need it for both, I'm just going to multiply both sides by -4 one time. So -4 on the left-hand side and -4 on the right-hand side. So I have -4x minus 4y minus 4z equals 8. So I'll take equation 1 and equation 2. Well, it's actually equation 4 now because I have a new equation. So 4 and 2. So that's -4x minus 4y minus 4z equals 8. And then 4x plus 2y plus z equals 1. X terms cancel. Then I have -2y minus 3z equals 9. So I'll take equation 4 and equation 3. So that's -4x minus 4y minus 4z equals 8. And then 4x minus 2y minus 5z equals 19. The x terms cancel, leaving me with -6y minus 9z equals 27. So I have new equations, 5 and 6. Okay. So I then have my two-equation system of equations. So -2y minus 3z equals 9, and minus 6y minus 9z equals 27. So that's equation 5 and 6. I am going to now eliminate the y term or variable. There we go. I was looking for the word. I'm going to eliminate the y variable. So I'm going to multiply equation 5 by -3. Okay. So let's get some more space to do that. So I'm going to multiply equation 5 by -3. So I have -3 times the left-hand side, and then -3 times the right-hand side. So that will give me 6y plus 9z equals -27. Okay. And so now I'm going to take that new equation and add it to equation number 6. So this is equation 7. So I have 6y plus 9z equals -27. And I'm going to add it to -6y minus 9z equals 27. Okay, so that was equation 7, and this is equation 6. So these cancel, and these cancel. So we have 0 equals 0, which is true. Okay, so because the variables went away in equation 3, and we ended up with a dependent statement, the system is consistent and has an infinite number of solutions. Okay? Awesome. So two distinct points in the Cartesian plane determine a unique line. Similarly, given three non-collinear points, we can find a unique quadratic equation or function whose graph contains the 3 points. So, in this example, we're asked to find the real numbers a, b, and c so that the graph of the coordinate function y equals ax squared plus bx plus c contains the points -1, 1, 0, -4, and 3, 5. So first we're going to substitute in -1, 1 into the function to obtain an equation in a, b, and c. So we know our quadratic function. Okay, we have our ordered pair, and we're going to substitute in this value. So y is 1, and then x is -1. So we have b times -1 plus c. So simplifying this gets us 1 equals a minus b plus c. Okay. So now we're going to substitute in 0, -4 into the function to obtain a second equation in a, b, and c. So we have our ordered pair. So we'll substitute in y, which is -4. So a times 0 squared plus b times 0 plus c. So -4 equals c. Okay. Now we'll substitute in our next ordered pair, 3, 5, into the function. So 5 equals a times 3 squared plus b times 3 plus c. So 5 equals 9a plus 3b plus c. So now we want to combine the three equations into a system. So we have a minus b plus c equals 1. We have c equals 4, -4 actually. And we have 9a plus 3b plus c equals 5. Okay. And we now want to solve this system. Alrighty. So since we know that c equals -4, we can use substitution and substitute that in right away into equations 1 and 3. Okay. So for equation 1, we have a minus b plus c equals 1. So we'll now have a minus b minus 4 equals 1. So a minus b equals 5. For equation 3, we have 9a plus 3b plus c equals 5. So 9a plus 3b minus 4 equals 5. So 9a plus 3b equals 9. Okay. So now we have our 2 system, a minus b equals 5, and 9a plus 3b equals 9. So we can use elimination, and we can eliminate b, or you can eliminate a, whichever one, but I'm going to eliminate b. So we have our new equations 4 and 5. So I'm now going to multiply. Let's see, I'm going to multiply equation 4 by -3. So I'll multiply -3 on the left side and -3 on the right side. So that's -3a plus 3b equals -15. And so that's in new equation 6. So I'm now going to take equation 6 and add it to equation 5. So that's negative 3a plus 3b equals negative 15. And I have 9a plus 3b equals 9. Oh, my b's don't cancel, so that means I made an error. So I actually should have multiplied this by a positive 3. Okay, so my signs here are going to change. All right, so 3a minus 3b, that's a positive 15. So then I can change this as well. So this will be minus 3 and then a positive 15. So now my 3b's can cancel. This leaves me with 12a equals 24. So then a equals 2. Okay. So now I know what a equals. So I can now back substitute. Since I already know what c equals, I'm going to use equation 1 and I'm going to substitute in both c and a. So a is 2, c is negative 4. And this will let me solve for b. So I'll have negative 2 minus b equals 1. So negative b equals 3. So b equals negative 3. Okay, so I know that c equals negative 4. I know a equals 2. And I know b equals negative 3. Okay. So my quadratic function is ax squared plus bx plus c. And that equals y. I know my a equals 2, my b equals negative 3, and my c equals negative 4. So the quadratic function that contains those 3 points is going to be y equals 2x squared minus 3x minus 4. Okay, and that's our quadratic function. And that concludes section 6.1.